All right, welcome back, guys. We're going to finish our kinematics 1D notes with acceleration. So that's the last thing we need to talk about. In the last video, we talked about position versus time and velocity versus time. But now we need to talk about acceleration, which is kind of the last dimension of motion. Okay, so acceleration is another vector quantity, meaning that we care about both the magnitude and the direction. So just like velocity, acceleration can be negative or positive. It could be both. The formula for the average acceleration is you take the change in velocity divided by the change in time, which we could also write as VF minus V naught divided by T. And if it's acceleration is V divided by T, then we know we can take the slope of a V versus T graph, and that would give us the acceleration. Just like with position is versus time, you can analyze that slope to get velocity. We can analyze a velocity graph to get acceleration. Okay, so just looking at this example graph, this is velocity versus time. So if we analyze the slope, we should get information about the acceleration. So from time 0 to time 4, it is a positive slope, meaning that the acceleration is positive or to the right. Then at the top, we have a flat velocity, and I kind of like to think of this as cruise control. We're going the same speed the whole time. We're not speeding up, we're not slowing down. So that would be like putting cruise control on your car. The slope is 0 here, which means your acceleration is 0. Don't confuse having 0 acceleration with having no motion. When things have 0 acceleration, there is still motion potentially. It's not a changing speed. We're not speeding up, we're not slowing down. So right there, you are traveling 8 meters per second. So you are moving, but you're just not accelerating. Then after the 7-second mark, we get a negative acceleration, negative slope. So remember that just means that it's accelerating to the left. Okay, so let's look at going from position to velocity to acceleration. So to get from position to a velocity graph, you analyze the slope. To get from velocity to acceleration, we do the same thing. We're going to analyze the slope of velocity to get our acceleration graph. We could also go backwards as well. Like let's say you had acceleration, but you wanted to know the change in velocity. To get from acceleration and change in velocity, we could find the area of the graph. And that can be proven if you look at the formula. If you want velocity is area times time, or sorry, acceleration times time, which is an area. If you're multiplying, it's an area. We could also take our velocity graph and we can find the change in position by doing the area of the velocity graph. So we can do the slope to go from position to velocity and velocity to acceleration. But then if you want to go backwards, if you have acceleration, you can analyze the area to find velocity, and then we can analyze the velocity graph's area to find the position. So you can go backwards as well. Okay, we'll talk more about graphing in a minute. So I'm just going to mention that, that you analyze the slope, or if you want to go backwards, do the area. So let's answer these conceptual problems. Do the acceleration velocity always have to have the same sign? No, your acceleration could be positive and velocity could be negative. Your acceleration could be negative and your velocity could be positive. This one just means you're moving left, accelerating right, because velocity is negative. Negative is moving left, but then you're accelerating the opposite direction. And then the other example would be if you're moving right, but accelerating left. Okay, moving right because velocity is positive, and accelerating left because acceleration is negative. Okay. Is it possible for an object to have 0 acceleration but a non-zero velocity? Yes. And I just spoke about that. We call that cruise control. So you're moving, but not speeding up or slowing down. Okay, so just because something has an acceleration doesn't mean it's not moving. Okay, so even if acceleration is 0, it could still be moving. It just means it's not changing its motion. All right, let's look at these quick graphs, one of the most common errors is that if you have a negative acceleration, it means you're slowing down. This is not true. A negative acceleration does not mean you're slowing down. Negative acceleration just means you are accelerating left. Okay, here's how you can tell if you're speeding up or slowing down. If velocity and acceleration are the same direction, that means you're speeding up. So think about it as them working together. You're moving right, but you're also accelerating right. That means you're speeding up to the right. If you're moving left and accelerating left, that means you're speeding up, but to the left. So if they have the same direction, whether that be right or left, if they are the same, they're working together, and that causes a speed up. If velocity and acceleration are opposite of each other, if they're opposing, if one's going right and one's going left, that's going to cause a slowdown. Okay, so that's how you can tell if it's speeding up or slowing down. Just because acceleration is negative does not mean it's slowing down. That is not true. Okay, so let's look at these scenarios. I'm going to focus on the velocity because that will tell me what direction I'm moving. So this guy, he's moving right because it's positive. And then the acceleration will tell me if he's speeding up or slowing down. So since it's pointing in the same direction as velocity, that means he's speeding up. It's not because it's positive, it's because they're pointing the same way. Here's a great example of that. We're moving left. And even though acceleration is negative, we are still speeding up because they are pointing in the same direction. So it's not about acceleration being negative, it's about them pointing and working together. Here's some examples of them slowing down. On this one, we are moving right, and that's all based on velocity. But since acceleration is opposing it, it's working against the car, we should be slowing down. Okay, and here's an example. Velocity is moving left, but it's accelerating to the right, which is causing a slowdown. Okay, let's try some graphing, and you kind of always want to begin at position versus time. Then you analyze the slope to get to velocity, and then you analyze that slope to get to acceleration. So you kind of always start at position. An object moving with a constant velocity of 5 begins at the point of origin. So let's begin at the point of origin. Constant velocity just means it should be a linear, and the slope should be positive. Okay, so I'm going to draw a positive slope, but linear. Then we need to analyze that slope. So the slope is positive and it's constant, which means our velocity should be positive. And it actually gave me a value as positive 5. And it should be constant, so we should have a flat line. Okay, now I need to analyze that slope so I can graph acceleration. So with the velocity being constant, it's staying 5 meters per second the whole time, so we have that flat line. And with a flat line, that means the slope is 0, so our acceleration is 0 the whole time. We're not speeding up, we're not slowing down, so my acceleration graph is along the axis. And that's the last thing you can do. There's nothing after acceleration, so it just is position, find the slope, velocity, find the slope, acceleration, and then that's the end of it. Okay, an object moving with a constant velocity of negative 2 meters per second that begins positive 2 meters from the origin. So we begin 2 meters in the positive quadrant, and then constant velocity, so we're going linear with a negative 2 slope. So I need to do a negative slope. Doesn't really tell me a stopping point, so you can stop at the axis, or it could just keep going infinitely because it didn't give me information about when it would stop. Okay, so let's take that slope. So this slope is positive, or sorry, this slope is negative. It's going down, and then it's constant. Okay, so let's take that slope. That is your velocity. So our velocity is negative and constant. So negative and flat. Okay, well, to get to acceleration, now that it's flat, the slope is 0, so acceleration is 0. We're not speeding up, we're not slowing down, right? We're moving constantly. Okay. This was supposed to say negative 2. I think it is that way in your notes, and this is just an old copy. So this one is almost the same. Constant velocity of -2, but it begins -2 from the origin. So let's actually start it in the -2. And it's going to have that constant velocity negative. So it's still going to have the same shape. We still have a slope that's negative and constant. So the velocity should still be negative and constant. Since it's constant, this slope is 0, meaning acceleration is 0, and then that would be it. Okay, it just takes some practice, but a lot of these are repetitive. And I put every scenario you could have. The only thing that they'll do differently is maybe they'll snippet several pieces of a graph together. So it'll be a big graph with different scenarios happening in different moments. But when you reach that situation, you just break it down piece by piece and just analyze each section individually, and then it will help you. Okay, so these are all the possible things you could have. An object starting position at its point of origin, so we're going to start here. The starting speed is 0, so if the speed is 0, it should start flat and be a 0 slope, and then accelerates with a +1, so we should curve increasing that slope since it's positive. Okay, so we're going to start at the origin. We're going to start flat because it stopped, and then we increase over time. So the slope starts at 0, but then the slope is positive and increasing over time. Okay, so take that slope information, translate it to velocity. The slope starts at 0, so we're going to start at a velocity of 0, and then it increases positively over time. It should increase at a consistent rate. All right, well, this slope is positive and constant, and so that's exactly what your acceleration should be. Positive, constant. Okay, in the positive quadrant, flat line. An object begins at the origin with a speed of -2, so we shouldn't start flat. We should start with a negative slope at the very beginning. But then it accelerates negatively, so we should be getting steeper since our acceleration is negative and our velocity is negative. It should speed up, but negatively. It should be traveling to the left. Okay, so let's translate that. An object begins at the origin. It's already traveling with a speed, but then it speeds up over time, so we get steeper and steeper. Let's make it a little bit better. Okay, something like that. For velocity, you already were negative at the beginning. Then you got even more negative as time went on. Okay, so this slope is negative, and it's constant. Okay, so if it's negative and constant, that means your acceleration is negative, and constant means flat. All right, let's do these word problems. So Ariel dropped a golf ball from her second story window. The ball starts from rest. So that is telling you something. Anytime it says it stopped or at rest, you need to do something with that information. So if it starts, that's a starting speed, and rest is 0. So it's telling me that at the start, the speed is 0. Hits the sidewalk 1.5 seconds later, so there's my time, with a velocity of 14.7 meters per second. Which actually there is a typo here because it's saying she dropped it from her second story. So the ball should be going downwards. If it's going down, it should end in a negative velocity because down is a negative direction. So that was just a small thing that we need to fix. Question here, what is the acceleration? Okay, so what I like to do is actually make a list of all my possible kinematic variables. And it helps you pick out a formula. Okay, so position I'm not given. The starting velocity is 0. The final velocity is -14.7. Acceleration is what we're looking for, so that's the most important thing. And then the time is 1.5 seconds. Okay, so you don't know position, so you're not going to use that. You can use the AP Physics formula chart. You could also use the formulas at the front of the notes. Where are they at? Right here. The only issue is don't use this formula unless acceleration is 0. So it has a rule that goes with it. If there is an acceleration, this formula does not work. So I would stay away from that formula. It's not even on the AP formula chart. It's just a way to explain what velocity is, because velocity is change in position over change in time. But this is if velocity is the same value the whole time. But if you have an acceleration, that's not true. And so this formula doesn't become true. All of these are all useful. They look different in the AP version. But that doesn't mean it's not the same equation. They just, instead of delta x, they'll say xf minus x naught and things like that. Okay, so use this formula chart. We're going to use this formula for the first one because we did not have change in x. So all three of these equations have change in x, change in x, change in x. So we can't use any of those. We're going to have to use the first formula. Okay, so let's do VF equals VI plus A times T. And I'm going to use V naught because that's what they use in the AP formula chart. Okay, so before we solve for acceleration by plugging in numbers, we really just need to derive an expression. So I'm going to rearrange it. My goal is to get A by itself. First, let's subtract V naught. And so rewriting it, I have VF minus V naught equals A times T. And then since I want A by itself, I'll divide by time. And that would be it. VF minus V naught divided by T gives you acceleration. Okay, but let me plug in my numbers so I have an actual answer. Okay, so let's type that in our calculator. Negative 14.7 divided by 1.5, and then you get negative 9.8. Let's check for reasonability. Is that a reasonable answer? So let's think about it. She was dropping a golf ball from the second story. The final velocity is negative. Final acceleration, we got a negative value. So let's just check if that makes sense. If velocity is negative and acceleration is negative, that means it was speeding up. So let's just decide if that's true. If something's falling from a building, is it speeding up? Which, yes, it is. So the negative is reasonable. Okay, and then 9.8, that's actually going to be a very important value to you throughout this whole year. Negative 9.8 is the acceleration of gravity on Earth, which we usually just represent with a little g. Okay, so everything on Earth falls with the same acceleration. The Earth pulls negative 9.8 meters per second squared on every object. Okay, so you'll know that from now on. This one was just showing that anything falling would give you that value. All right, let's write our variables. Delta x, v naught, vf, a, t. How long would it take Jess with an acceleration negative 2.5 meters per second squared to bring his bike with an initial velocity of 13.5 meters per second to a complete stop? So that final velocity is 0 meters per second. We do not know position, and it asks how long would it take. So we are looking for time. So we don't want change in x, and we need an equation with time. Well, it looks like it's going to be the same equation as I just used, which you can look at the front page to decide for yourself. But this equation, it doesn't have change in x because we don't have that. And it also has time, which I do need. Okay, so solve for time. Subtract v naught. Vf minus v naught equals at. And then to get time by itself, we're going to divide by acceleration. Okay, so Vf minus V naught divided by A will give you T. Let's plug in values. So Vf is 0 minus 13.5 divided by negative 2.5 equals time. So let's see what that is. And it looks like the time is 5.4 seconds. Okay, checking for reasonability, your time should be positive. time cannot be negative unless you're a time traveler. So your time should be positive. If it's not positive, check the signs on in the equation. Make sure you use the right negatives or positives. And remember, it's VF minus V naught. So that could have been the issue, but that is reasonable. Okay, so let's try this last problem. Okay, so it says a car starts from rest. So if it starts from rest, the initial velocity should be 0. It accelerates uniformly over a time of 5.21 seconds. So I already put the time there. For a distance of 110 meters, so that's change in x. Remember, distance is change in position. And then acceleration is what we're looking for. So I actually don't have final velocity this time. So let's go to our equation chart. You need to find something that does give you acceleration, but doesn't use the final velocity. Okay, so let's look at this formula chart. So the first equation does have VF, so we can't use that. Next equation could work. This equation has VF, that won't work. And the last one has VF, that one won't work. So it looks like this is our choice. So let me go write that down. Okay, so we're gonna do change in x equals v naught t plus 1/2 at squared. Okay, so rearrange and solve. We need acceleration, so I need to solve for acceleration. V naught times t, I can move that all over. It is being added right now, so let's subtract. Okay, so that went away. And then, so I have delta x minus v naught t on the left-hand side, and on the right-hand side, I have 1/2 at squared left. Okay, so still working our way to a, we have 1/2. Remember, think of that as 1 divided by 2. So if we're dividing by 2, multiply both sides by 2. So we have 2 times change in x minus v naught t. And then on the other side, we still have at squared. Okay, the acceleration is not being squared, so we don't have to take care of the square. We should not be square rooting. We can just move t squared to the other side altogether. T squared was being multiplied, so divide. Okay, so a equals 2 times delta x minus v naught t divided by t squared, and that would be your answer, but we're going to plug in our numbers. Okay, so let's type that in. 2 times 110. And it looks like our acceleration is 8.1 meters per second squared. Okay, let's see if that makes sense. So let's look at our velocity. It was moving, it started from rest and it accelerated uniformly over time. Well, we weren't really given any information about our velocity, so I guess I can't check for reasonability, but we would assume the velocity is increasing positively, our acceleration is positive, so it should speed up. And that's what it says. It starts from rest and accelerates over time. So it's a bit hard to check for reasonability on this one, but seems reasonable enough. All right, so I think there's one more lesson for Kinematics 1D. We need to talk about relative motion, but I'll do that in a separate video. That is it for Kinematics 1D. We have position, we have velocity, and we have acceleration. Make sure you know the difference between a scalar quantity and a vector. So remember that your scalars, they only care about the magnitude. Okay, so don't pay attention to the direction. There's no sign. If it says -5 meters per second, for instance, the magnitude would be 5 meters per second because we don't want to pay attention to the negative. So take like the absolute value. Whereas vector, you care about the magnitude and the direction. So Negative 5 meters per second, that is the vector quantity. Cares about both the sign and the number, okay? So scalar, just the number, vector, number, and direction. And then we have kind of one of each we have displacement and we have distance. We have velocity and we have speed. So those are different words for the scalar and vector. You need to make sure you know scalar is distance and speed. And then the vector words are displacement and velocity. And then you also have acceleration. Acceleration is a vector, but there is no scalar version of acceleration. It's just acceleration. Okay, and then make sure you practice your graphing. There's graphing posted on Google Classroom. You can play the matching game. You can run the PhET simulation, but practice your graphing skills. Okay, so that's it for 1D kinematics. I'll do a separate video for relative motion later.